All right, we're at section 24.5, electric potential due to continuous charge distributions. This is, uh, there's, uh, we looked at electric field from continuous charge distributions, and this is similar. It's not the same, but it's similar. Some of the examples are that you'll see are you saw them in chapter 23 also. Let me hide my uh, image so as not to interfere. So electric potential due to continuous charge distributions. Now we have these, there's a point P. We want to know the electric potential here at this point from all these contributions, DQ1, DQ2, DQ3, and they're all at different radii, R1, R2, R3. And we learned from equation 2411 that V equals KE Q divided by R, and we're going to use that. dV equals KE dQ divided by R. And so V is equal to the KE, the integral of dQ divided by R. And the problem solving strategy for these is to conceptualize, categorize, analyze, and finalize. So in the conceptualize, think carefully about the individual charges or the charge distribution you have in the problem, and imagine what type of potential would be created. Appeal to any symmetry in the arrangement of charges to help you visualize the potential. Uh, Under categorize, are you analyzing a group of individual charges or a continuous charge? A continuous charge distribution. The answer to this question will tell you how to proceed in the analyze step. And in the analyze step, when working with problems involving electric potential, remember that it is a scalar quantity. So there are no vector components to consider. Therefore, when using the superposition principle to evaluate the electric potential at a point, simply take the algebraic sum of the potentials due to each charge. You must keep track of signs, however. As with potential energy in mechanics, only changes in electric potential are significant. Hence, the point where the potential is set at zero is arbitrary. When dealing with a point charges or finite size charge distribution, we usually define V equals zero to be at a point infinitely far from the charges. If the charge distribution itself extends to infinity, however, some other nearby point must be selected as the reference point. Um, so if you're analyzing a group of individual charges, use the superposition principle. Um, if you're analyzing a continuous charge distribution, replace the sums for evaluating the potential at some point P from individual charges by integrals. Um, to obtain the potential from the electric field, another method is used to obtain uh, is you start with the definition of the potential difference given by equation 24.3. If E is known or can be obtained easily, such as from Gauss' law, then the line integral of E dot ds can be evaluated. And then finalize. Check to see if your expression for the potential is consistent with your mental representation and reflects any symmetry you noted previously. Imagine varying parameters such as the distance of the observation point from the charges or the radii or the radius of any circular objects to see if the mathematical result changes in a reasonable way. Looking at extremes is a common method uh, for uh, uh, analyzing your results. Okay, and I think that's the end of this section, short section, but valuable. So we'll stop here and go on to section 24.6 in the next video.